Welcome back, everybody. In this section, we're going to be working on producing confidence intervals for the standard deviation and variance. So far, we've done confidence intervals for proportions and then mean. And now we're doing the same basic thing, but it's for standard deviation and variance. We will have a new table for this section called the chi-squared distribution. There's a copy of that posted on Canvas, also in your textbook. We'll go over how to use the table in just a few minutes. The first thing, though, is to lay some groundwork and talk about some basics having to do with the variance and standard deviation. We had a point estimate for both the proportion and the mean. The sample variance, S squared, is the best point estimate for sigma squared. Also, the standard deviation of the sample is often used to estimate population standard deviation, although we saw back in chapter 5 that it is a biased estimator. I'd mentioned we need a new distribution to help us find these confidence intervals for variance and standard deviation. It's called the chi-squared distribution. So it's named after this Greek letter that looks kind of like a fancy capital X. It's the Greek letter chi. And the formula for the sample statistic is chi-squared will be n minus 1 s squared over sigma squared. All right, so there's the chi-square formula. We mostly won't be using that formula in that exact form in this section, but in later sections we will. So one thing that is important about the chi-squared distribution is that unlike the normal distribution and the t-distribution, it's not symmetric with respect to a mean. The distribution is right skewed, and all the values of chi-squared are positive, which you can see by looking at the formula. The formula in 7.5 is n minus 1, which is positive, times s squared over sigma squared, which is a bunch of squared numbers, and so they're positive. So all of the chi-squared values are positive, and their distribution is also right skewed. The shape of the distribution, like the t-distribution, is going to depend on a degrees of freedom, which will be n minus 1, just like in the t-distribution. So in the picture here, degrees of freedom 10, you can tell that one is taller and more right skewed. At degrees of freedom of 20 is less extreme looking, it's less tall and also less skewed. Since the chi-square distribution isn't symmetric, we're going to need two different critical values, a chi-squared left and a chi-squared right. So we'll have to look up two values in a table as it turns out. So this we'd mentioned already, the chi-square distribution is not symmetric, and as the number of degrees of freedom increases, the distribution does become more symmetric. The values of chi-square can be 0 or positive, but are never negative. Okay? And the shape of the distribution is different for each number of degrees of freedom. Okay, so that's the basics. And what's next, we need to take a look at how to read the table. So the chi-square distribution isn't symmetric, as we've mentioned. So we're not going to be able to calculate one value for E and then just add and subtract it from S squared. We'll need to do separate calculations for the upper and lower limits of the confidence interval. So let's try. Suppose that we want a 90% confidence interval for sigma squared with a sample size of n equal to 9. We're to find the left and right critical values. We're not going to get the whole confidence interval at this point. We just want to focus on being able to find critical values. The degrees of freedom will be 9 minus 1 or 8. And then our table will give us the critical values. But I'm going to start by making a little sketch if we want a 90% confidence interval, then that means that there's 10% left in the whole distribution. 0.05 will be here on the right side, and 0.05 will be here on the left side. We need two different critical values. Here's what the chi-square distribution looks like. Like the t-distribution, down the left side, you'll see a degrees of freedom. Here I've just put the first 10 rows because that's all we need for this problem. And then the columns are areas. Notice the first 5 columns, there's a separator in the table that separates from the second 5 columns. In the first 5 columns, they range from 0.90 up to 0.995. And then in the last 5 columns, it ranges from 0.005 to 0.10. And this table always tells you the area to the right of the critical value. So unfortunately, like our Z table, we worked from the left, area from the left. This one, it's always area on the right. So let's try. For our chi-squared right, we'll start with right because it's easier. Our chi-squared right is here. Our degrees of freedom is 8. So we'll look under the row 8. At this critical value, we should have an area of 0.05 to the right. So looking across the top, 0.05 is here. This is always the area to the right. 0.05 to the right, 15.507. Next, we want chi-squared left. So at this critical value, how much area is to the right? 0.90 plus 0.05. 0.95 is the area to the right. So we'll look in a column marked 0.95 and go down to the same number of degrees of freedom, 2.733. And that will be our chi-squared left. And the 15.507 was our chi-squared right. So take some time to work through this example on your own and make sure that you can see where the values are coming from in the table. Now we're going to try another example. In this one, let's say that we're going to try to find a 95% confidence interval for the variance, and we have a sample size of 23. We'll find the left and right critical values. As before, let me start with the degrees of freedom. That is going to be n minus 1, and so it will be 22. So we'll be working off of row 2 in our chi-square, 22 in our chi-square distribution. We want a 95% confidence interval. So the whole area under the curve is 100%. We've got 95% in the middle. That leaves 5%. Putting that into 2 equal parts, we'll have 2.5% in either tail. So for chi-squared right, we will look on the row 22, degrees of freedom 22. We need an area to the right of 0.025. Where those meet, sorry, it's kind of blurred by the copyright, 36.781. For chi-squared left, there's 95% of the data in the middle, 2.5% in the right tail, so it's 97.5% in the right to the right of our critical value. So our critical value here is going to be 10.982. Okay. You'll notice when we did this that the two values we needed ended up in the middle of each group of 5 columns. In the first group of 5 columns, we used the middle column. In the second group of 5 columns, we used the middle column. But we have our two critical values. Okay, now that we've practiced that, we're ready to start coming up with a confidence interval. So as always, the fine print. The usual definitions, we have sigma is the population standard deviation, S the sample standard deviation, N the sample size, the chi-squared left and right that we saw, our E margin of error, and then we also have the variance for the sample and population. Requirements for us to do this, we need to have a simple random sample. The population needs to be normally distributed, even if the sample is large. The requirement that it's a normal distribution is more strict here than when we work on like proportion or the mean. So departures from normality can result in kind of big errors here. So we want to be really careful to check for normality. So the formula for the confidence interval, that we're not going to be able to use the plus minus notation for this because our E is not the same, right? Because our two critical values are different. So the two formulas we have, one for standard deviation and one for variance, I definitely wouldn't try to memorize these as two separate things because the standard deviation is just the square root of the variance, right? So let me take a look at the variance one first. The variance is in the middle. There's two less than signs on either side, then two fractions on either end. The numerators are both n minus 1 s squared, n minus 1 s squared on both. And then the denominator of the fraction on the left is chi-squared right. The denominator of the fraction on the right is chi-squared left. And that's not there just to kind of confuse you. I promise. What you want to think about here is remember that in our chi-squared distribution, here, all of the values in our chi-squared distribution are positive, right? So the table starts, sorry, I'm dizzy. The chi-squared values start at 0 and go up. The further to the right, the bigger they are, okay? But all are positive. So in here, our chi-squared right and our chi-squared left are always positive values. And thinking about fractions, if you have the fraction 17/20ths, I'm just making this up, okay? 17/20ths versus 17/11ths. Which one would be a bigger fraction? 17/11ths is bigger, right? If you have two fractions and the numerators are the same, the bigger fraction has a smaller denominator. Let me use maybe friendlier fractions for that. Let's say that you were going to go out for a party and buy like 3 pizzas. If you have to split them among 10 people, you're getting less pizza than if you have the 3 pizzas split among 4 people, okay? So the bigger denominator will make for a smaller fraction. Our chi-squared right is always to the right. Chi-squared right is always bigger than chi-squared left. So that's why in the fractions, the smaller fraction has chi-squared right in its denominator. The bigger fraction has chi-squared left in its denominator. When you see the left and rights here, you want to remember that left and right is off the picture, not off the inequality. Because if you go off the inequality, it's backwards. Chi-squared right is on the left fraction, chi-squared left is on the right fraction. All right, so now we're ready to actually try it. So here's this data set 3, and Appendix B includes a sample of 106 body temperatures having a mean of 98.2 Fahrenheit and a standard deviation of 0.62 degrees Fahrenheit. We're to make a 90% confidence interval estimate of the standard deviation. All right, so let's see. So there's several pieces that we're going to need here. I'm going to need a couple of critical values. So allow me to draw a rough sketch of that chi-squared distribution. So we wanted a 90% confidence interval. That means that 10% is left in the two tails, half of it in each tail. So we'll have a chi-squared right we got to look up, and a chi-squared left we'll have to look up. So here our n is 106. That was our sample size. So our degrees of freedom is going to be 100. So let's take a look at the table. So our table only goes up to 100. So we're going to use that. That's basically all we've got, right? So we needed 0.05 in the right. So where's 0.05 in the right? That's here. We'll go all the way to the bottom. That will be 124.342. And then for our chi-squared left, 0.95 is on the right. So where's 0.95 on the right? Right here. Go all the way to the bottom of that column, 77.929. Okay, and then just to make sure here, 77 is less than 124, so it had better be the one that is on the left. Okay, so then we're coming up with a confidence interval for the standard deviation. So that will be a couple of square roots. Our signal will be inside. The radicands are each fractions. They're both n minus 1 s squared on the top. And then down below, we'll have chi-squared, which one? It's chi-squared right on the left and chi-squared left on the right. That takes a little getting used to, but you'll be okay. So here, n minus 1, that's 105. Our s squared, that will be 0.62 squared. Chi-squared right is 124.342. And then the upper end, the numerator here is the same, 105.62 squared. Chi-squared left, 77.929. Okay, so let me, all right, so I've run that through the calculator and I've ended up with 0.570 up to 0.720. So we could say that we're 90% confident that this interval contains our sigma. Okay, try another example. So here, the chapter problem for chapter 3 includes the numbers of chocolate chips in a sample of 40 Chips Ahoy regular cookies. The mean 23.95 is given. I don't think we use that. The standard deviation is 2.55. We're to make a 90% confidence interval for the standard deviation. And again, we have S. All right, so let's go ahead and get started. Our sample size was 40, and so our degrees of freedom will be 39. So picture. We want a 90% interval. So we'll have 0.05 in the right tail and 0.05 in the left tail. So we'll need to go get our two chi-squared values. All right, so in this problem, our degrees of freedom is 39. Unfortunately, our table doesn't have a row 39 in there. When you get near the bottom of the table, it's skipping by tens and then bigger values as you get further down. So we'll have to decide what to do here. So we're going to need 0.05 in the right tail. So that's over here. And then 0.05 in the left tail. So we'll need the 0.95 column. So taking a look at these two columns especially, taking a look here, 30 would be 18, 40, 26.509. 39 is much closer to 40 than it is to 30. So we're going to go ahead and use 40 just because we haven't got the row for 39. The further down the table you go, you'll see that there's less difference in here. So it's not going to make a giant difference. If you want, you can recompute this for 30, 40, and 50 and see how much of a difference it's going to make. So our chi-squared right is going to be 55.758. Our chi-squared left, 26.509. So then our formula for standard deviation, n minus 1 s squared over chi-squared right sigma, and then same basic square root on the other side, only it's chi-squared left. All right, so then we just need to fill in everything we have for that. We'll have 39, that's our n minus 1. Our sample standard deviation was 2.55. And then we have 55.758. And then the upper end, same numerator. And we'll have our chi-squared left, 26.509. I wanted to mention before we go any further that these numbers, chi-squared left and chi-squared right, that's the exponent of 2 there is part of the name of the number. So when you're doing this formula and it's got the chi-squared right and chi-squared left in it, that's just the number you've looked up in the table. It would be wrong of me to go through and square those, okay? I don't want to do that because this exponent of 2 is just part of the name of the number. So don't square those two denominators in there. Okay, in fact, this is all we need, so let me calculate that for you. All right, so our 90% confidence interval for sigma worked out to be 1.99 up to 2.89. So that gives us a sense of how variable this number of chocolate chips in Chips Ahoy cookies is. All right, so one more set of examples. So we had used this example of the weighting lines in banks a couple of times as early as chapter 3. So we're going to do it once more here. Here the values are the waiting times for 2 different banks. In Jefferson Valley Bank, the customers enter a single waiting line where when people go to the head of the line, they then are helped by the first available teller. In the second part, we're looking at Bank of Providence, where people enter individual lines for each individual teller. And in each of part A and B, we're to construct a 95% confidence interval for the standard deviation. The n in both cases is 10, so our degrees of freedom will be 9. And then I've calculated the sample standard deviation for us to save us a little bit of time. So let's get started on these. All right, so I've gotten us started. For both, we're coming up with a 95% confidence interval. So I've started with the sketches. We've got 0.95 is the area in between. So the right tail of if 95% is in the middle, that leaves 5% in the two tails, or 2.5% in either tail. That's true of both. Since our sample size is 10 for both banks, the degrees of freedom will be 9. So we'll be looking at row 9 in our table. The area to the right is 0.025. So our chi-squared right is 19.023. That's true for both because the critical values are determined by the sample size and our degree of confidence. For the chi-squared left, it will be 97.5%, so we'll have 2.70. That will be for both. Okay, so I've started filling out the formulas for these. So the chi-squared right is 19.023. That was for both. The chi-squared left was 2.70. That's for both. I'm doing Bank of Providence on the right and Jefferson Valley Bank on the left. So Jefferson Valley Bank was first. Their S was 0.477. We'll have to square that. For Bank of Providence, we saw that it was 1.822. All right, so now we just need to run the calculator. All right, so putting these two into the calculator, our 95% confidence interval for Jefferson Valley Bank was 0.328 up to 0.871. For Bank of Providence, it was 1.253 up to 3.327. So one thing that is interesting about producing these two intervals is you'll notice that they don't overlap at all. So that's pretty suggestive that the two standard deviations are actually really different from one another. So one other thing I would like to do is show you how to use StatCrunch to find the confidence interval for the variance and standard deviation. So to do that, we will go into Stat, and then you want to go down to Variance Stats. We have one sample. And from here, with this particular problem, we were given the times for the two banks. So if you want, you could use the data if you go ahead and put that into columns of our worksheet here. To save time, and since we already have the standard deviation, we're just going to go with summary. And then one thing that you got to be careful about on this is that we're trying to find for the standard deviation. The StatCrunch is set up to do variance. So we're going to do Jefferson Valley Bank first, okay? For this one, it's expecting us to have the sample variance. So we saw the standard deviation was 0.477. So I need to square that first to get the variance. So that's 0.227529. And then our sample size was 10. We're doing a confidence interval, and it was a 95% confidence interval. And notice this will be a confidence interval for the variance. Okay, so that's what we get for our variance. So in taking a look, we'll need to end up finding the square root for both of those so that we can compare them against the one that we have already obtained. All right, so now let's go ahead and do it also for the Bank of Providence. So once again, we'll go down to Stat, then Variance Stats, one sample with summary. Sample variance. Again, the standard deviation is 1.477. 822. So we'll need to square that to get the variance. That's 3.319684. Our sample size was 10. And then we're getting a 95% confidence interval for the variance. So let's calculate that. So here's what we get for our variance for the second bank. So we're going to copy that over and then we'll be able. All right, so here we are back to looking at the results we'd obtained before. So again, it's key to remember that the process that we were following, we found the standard deviation confidence interval. What StatCrunch is going to give you is the confidence interval for sigma squared, which is why when you look at the output on the computer, it looks like it's so much different than what you got in calculating by hand. For example, this upper limit was 0.7583, and in comparison to what we'd obtained was 0.871. And the reason for that, again, is that the computer is giving us the squared values. So whatever you get out of the computer, you're getting variance. So take the square root of it to get the standard deviation. I hope that all makes sense. Let me know if you have any questions. That does finish this section for us. Have a great day.